Thank you. So today webinar is about the usage of cloud technology and GeoAnalytics. As Reem mentioned and introduced me, I'm responsible for the space data system within MBRC. Previously worked on leading the ML Smart Mission Science Data Center, where we perform data processing and data management. Joined a couple of projects, including DMSAT, KhalifaSat, MBZSat within the MBRC different missions that we have. Previously, I also worked on geospatial data analysis, as well as some software development for the ground operation and ground segment of different missions within MBRC. So the agenda for today, first we'll start with introduction about geospatial data, and then we'll look at the characteristics of geospatial data, Earth observation data, and we'll look at how increasing the size of Earth observation data will impact the way that we interact with the data, the way that we analyze the data, and so on. And then we look at the cloud computing technology, brief introduction about the services provided by cloud computing, and then how can the cloud computing technology help spatial data to perform data analytics, including change detection, airbill monitoring, and so on. And then at the end, I'll give some examples about companies that utilize cloud computing to perform GeoAnalytics. So, satellite images captured from Earth observation missions getting higher and higher in terms of not only the resolution, in terms of the quality, in terms of the data volume. We start, for example, with an MBRC with the BISAT-1, which is 5-meter resolution. And then we had the BISAT-2, 2.5 resolution. We keep enhancing the resolution of the camera that is on board the spacecraft. KhalifaSat, we have 1-meter resolution images that captured by the camera on board KhalifaSat, and so on. So you see how the resolution of the satellite images get better and better. Now we can have, for example, the 5-meter resolution camera on board nanosatellite or microsatellite. So how easy we can onboard high-resolution images, high-resolution payload into smaller satellites. And when you increase the resolution, eventually you will end up with higher data volume for satellite images, and you will end up stepping into big data era. The way that we deal with big data is totally different than if you have data or satellite images in megabytes. Now, agency currently working on bringing the user to the data, not data to the user. So you'll see later on how agency work on that. They want the analysis to be performed closer to the data, so that the people who's performing the analysis doesn't require to download a huge amount of data to their workstation, for example, to work on the data. This allows for increase the speed of performing the analysis and performing the analysis across a bigger amount of data. So, for example, instead of processing just one region of interest at one time, you can perform analysis across multiple regions. So, let us look at the characteristics of big Earth observation data. First, as I mentioned, large volume. A single remote sensing image can easily reach right now to 1 GB, which is resulted on explosion and volume of mission dataset. Some missions already reaches petabyte of data. So, for example, NASA Landsat mission, ESA Sentinel missions, this mission already reaches petabyte of data that being collected, downloaded, processed, and ready for analysis. Great variety. Different missions have different sensors and great different generate different data formats. So you could have right now within a smaller satellite a payload that capture RGB images. At the same time, you can have a different type of payload, for example, generate infrared data. So you have different type of data. Also, at the ground segment, you perform processing, you generate different data format for different missions. So some missions generate GeoTIFF data format. Some missions they use JPEG or high GeoTIFF or JPEG 2000. So you will end up with having different data formats for maybe for a single mission. The third one is the multi-resolution missions payloads evolving and resulting in enhancing spectral as well as spatial resolution. So as I mentioned, currently people working on generating, processing, analyzing sub-meter resolution images at this time. So as really now people looking for lower resolution, maybe for a larger area, they are looking for lower resolution, but for a specific area, they want to have more information in the data to be analyzed, to be generated. Time series. Different missions have different temporal resolution. So, for example, some mission cover the entire Earth within 5 to 6 days. Some mission generate data for the entire Earth within 2 days. So you will end up with having different temporal resolution for different missions. So how you deal with this? Global scale mission can capture larger Earth services area from the space. So some mission just images the entire Earth at a single image capture. Some mission, no, just 12 kilometer by 12 kilometer. So different global scale, different data monitoring. And at the end, last data intensive data processing rate lower than data acquisition and transmission. Now, some missions, they have raw data that's not been yet processed, captured months before. This is because the data acquisition rate is very, very high, and the infrastructure supporting to perform data processing is not, cannot reach the speed of data acquisition. So we have lots of data that's not been yet processed to a useful kind of data that can be analyzed by different analytic agencies. So for that kind of characteristics, we need a massive infrastructure, and cloud computing can provide services that will help agencies to perform analysis on data, even considering the high data volume, the different data format of captured data, and so on. So what is cloud computing? Cloud computing basically resources and services provided through the internet. So you will easily can access cloud computing resources, for example, on somewhere sitting in cloud provider data center. You can spin up machines with the specs that you want within minutes. So a very fast amount of computing resources needed, and you will end up by paying for what you use, on-demand payment. So if you use a machine with low specs, you for a certain time, for 2 minutes, you pay only for the 2 minutes. If you use, for example, the high specs machines, for example, within 1 hour, you pay just for 1 hour. And we within MBRC, for example, we utilizing that kind of on-demand resources acquisition from different cloud providers to perform either data processing or data analytics for mission data that we generate. So you don't need to buy expensive hardware infrastructure to accomplish computing and storage needs. As you have more missions, as you have more higher resolution missions, you will need to enhance your infrastructure, enhance your computing resources, enhance the storage that you need. The better resolutions, the more data volume you generate. The more data volume, you need to add more storage, and you need to upgrade your storage at the same speed as your satellite is capturing images, which is a bit difficult with on-premise kind of solution or on-premise kind of infrastructure. However, cloud computing allows you to acquire resources, either storage resources, computing resources, whatever resources you want within minutes. A few clicks, you have, for example, very high specs computing resource or very large volume storage. There are different well-known international cloud computing providers. The famous one are Amazon Web Service, Microsoft Azure, and Google Cloud. So there are lots of other cloud providers internationally, including Alibaba, Huawei, and so on. Computing as a service. Most cloud providers deliver the following main services. The first one is software as a service. Basically, here you require licenses to use an application. One example of this is mailing services. If a company decided to have a mailing service from a certain cloud provider, they purchase only the license for that, and the mailing service is available to the enterprise company. Software can be accessed through the internet instead of installing in your computer. One example related to geospatial analysis is basically Esri products. You can easily now buy or purchase a Esri license, and the products not installed in your machine is installed in the cloud. Having that product installed in cloud, the underlying infrastructure and computer resources can be dynamic. So sometimes you're just browsing satellite images through Esri products, but sometimes you need to perform sophisticated kind of analysis. So you need to enhance the hardware underlying the Esri product. So this is more dynamic, more flexible when you have that kind of mechanism applied. Platform as a service, the platform has everything subscribers need or company need to build, test, and launch their own application. So this is a different type of services provided by cloud providers. So no control on processing, storage, or networking. You have the platform for you ready to install your software. So for example, here we have Google App Engines, where everything's available for you in terms of hardware, in terms of networking configuration, in terms of storage that you need. And then you install and utilize the libraries provided by the cloud provider to install your application. Another example, AWS Lambda, which is a serverless kind of service provided by AWS. And the third one is infrastructure as a service. Here you have more flexibility in terms of the infrastructure that you need. So you can change the specs of the computing resources. You change the amount of storage that you need, networking capacity or configuration, and so on. So these are the main services provided by the cloud provider, and you see what you're looking for, what is your need, and then accordingly you choose the services that you need from the cloud providers. Now, how we link cloud computing with spatial data? Excuse me. When we look at from bottom line, we have the infrastructure. I think here, yeah, so we'll explain here. Um, we have the infrastructure provided. So we have AWS that can provide, for example, the infrastructure you need, or Microsoft Azure and so on. Here, as I mentioned, you leverage an on-demand large amount of computing resources and services. This is the infrastructure. And then on top of the infrastructure, you have the Earth observation data. Free access service to Earth observation data. Usually, cloud provider build a flexible framework for global and multidisciplinary data sharing and Earth observation. So, for example, we have Google Earth observation system, and we have AWS open data. So within that registry, you have different agency that capture and provide geospatial data. They put that kind of data into the cloud provider so that the user of their data, they don't have to get the data from the cloud. They perform the processing, they perform the analysis on the cloud closer to the data. On top of that, we have the algorithm model libraries. Algorithm that you need to perform GeoAnalytics. So for example, ArcGIS or Google Earth Engine, they have lots of algorithms that you can utilize, already been developed for you to utilize in order to analyze the satellite images. And on top of that, you have processing and computation resources. Similarly, processing and computation libraries and services provided by cloud providers to process your satellite images. Still, the example is ArcGIS processing algorithm that already been provided. Google Earth engine that you can utilize in order to use the processing and computation resources available. Finally, at the very top is the system and application. This is fast growing patterns. This is where different companies, they develop a system or application related to geospatial data analysis. So, for example, a company that building, for example, water body monitoring. So this is kind of application that sit on top of these underlying available resources. Another example, Spatial Hadoop, which is an open source system, was formed, complete logical services from geospatial computing to application. So now we'll see different example of cloud computing usage for GeoAnalytics, different companies that use the cloud for that kind of purpose. First example is Digital Earth Africa. The solution is built to help GeoAnalytics service deployed at AWS, including changes in vegetation and land service, food security, monitoring mangroves in Zanzibar, and so on. This will help data users across the continent gain fast access to petabyte of decision-ready satellite data. So the satellite data that they receive from Landsat, from Sentinel information, they are very huge amount of data in terms of petabytes, so hundreds, thousands of terabytes. And they utilize the cloud to make this kind of data analysis ready, been already analyzed and displayed to decision maker in order to see and monitor the changes in vegetation, having some analysis related to food security, monitoring the mangrove, and so on. The second example is Mara Space Technology. This is a South Korean kind of company that builds nanosatellites constellation and provides satellite data services to let customers quickly identify and address issues like changes in climate condition and disaster recovery to improve life on Earth. They use small satellites to generate a very high resolution images with the help of different resources provided by AWS, for example. So they deliver in minutes instead of hours data that's been already processed and ready to be analyzed. Quickly process, transfer, and share large amounts of data. AWS services like API Gateway, AWS Lambda, DynamoDB. These are some many services provided by the cloud provider, and they utilize it to retrieve data at high speeds and deliver critical insights to customers in minutes instead of hours. Usually, processing or performing processing into satellite data that's been downloaded from spacecraft needs hours to be processed, and then you need to share that kind of processed data to the customer. So you might end up with some networking issue in sharing the data. So using cloud cloud technology will minimize the challenges that you might face if your processing environment happening on-premise. They develop cloud-based, simple-to-use platform for customers to perform GeoAnalytics. So on top of the data provision, they build a platform ready for customers to analyze the data that they generate on the cloud. So the customer doesn't have to retrieve or download the data from the cloud. They just use the platform in order to analyze the satellite images that they generate. And also they are using some AI technology provided by AWS, which is the AWS SageMaker managed services, in order to generate super resolution satellite images. That resulted into 3 times better satellite resolution. The third example is Natural Resources Canada. They migrated 3 petabytes of data to the cloud. So this is a very huge amount of data. Serving that data to the end user is a bit difficult. So you need to have a very fast access kind of storage. You need to have a very high throughput kind of network that can share the data, at massive data with the customer. But migrating that amount to the cloud will minimize these challenges. The migration helped them to modernizing its geospatial offering at a faster pace, so they can quickly share the data to the customer. They use also AWS Cloud Pipeline to manage upgrades, batches, and other technologies changes, along with AWS Cloud Code Build, AWS Cloud Formation, and AWS System Manager. So when you use the cloud, you go for different managed services that provided by cloud providers in order to enhance your utilization of the cloud. Example number 4, Blue Dot Observatory. They leverage AWS Open Data and the cloud monitor at-rest bodies of water. They develop open source algorithm that checks for newly available Sentinel data, Sentinel specifically Sentinel-2 data, in AWS Open Data Program. So AWS Data Program has different data repository for different satellite providers. So they have Sentinel initiative available as the Open Data Program. They have Landsat data already available to be accessible at their Open Data Program, and so on. So this company utilizes Sentinel-2 data to monitor, they call it at-risk bodies of water. So lakes that can easily dry. The process the data using Sentinel Hub services to filter out any cloudy kind of data, interrupted kind of data, and identify water pixels. Um, then they execute a water detection algorithm over water bodies from their database on dedicated Amazon EC2 instances. Once they generate the data out of the algorithm, they store it in S3, and they build also on top of that a platform called Observatory solution to retrieve data using web services and display the satellite images on that kind of solution. The fifth example is from MBRC. MR Smart Mission Science Data Center fully deployed at the cloud from day one. We have all required resources and infrastructure needed to perform data management and storage, to perform data processing, so generating level 1 and 2 products out of the raw data that we receive from the Mission Operations Center of the mission. And we also perform data dissemination and disseminate the high-level products that's useful for science community through utilizing the cloud services. We heavily utilize cloud serverless technology and microservice technology to perform data management and processing activities. These are all automated and event-driven kind of processing that's happening once we receive the raw data from the operation center, as well as some kernels that's required for processing, and then we generate high level of processing, and we kick off automatically the processing pipeline to generate high level of products that at the end eventually will be shared to the science community. Cloud-based data analysis environment has been developed to help mission scientists to analyze mission scientist analysis algorithm to run the cloud without the need to download the science products to the analyzer workstation. So we created a analysis platform, and we make it available to the mission scientists in order to perform their analysis algorithm in the cloud closer to the data without the need to download the data to their workstation. So they don't have to download a huge amount of data that we have at a storage repository to perform analysis. They just upload their algorithm, and we provide them with the resources, the infrastructure, the computing resources required for them to run their algorithm software to analyze the data that we generate from the mission. A second example from also MBRC is DMSAT mission. Similarly, we have the cloud technology being utilized to perform a data processing and management task for the mission data. We automate the data processing pipeline from level 0 data all the way to level 2 products. We integrated the pipeline that's available in the cloud with the operation environment that we have at MBRC to receive raw data, and then accordingly we kick off the processing pipeline for both instruments that we have on board the missions. So this is a kind of seamless integration between the environment that we have on-premise with the environment that we have at the cloud. So this is what I have. Thank you for listening, and I'm ready for answering the questions.